everyone. So today we're going to be starting off chapter 4 with pretty much a kind of a review of certain aspects of phase chemistry. So this chapter we're going to be talking a lot about the various phases of chemical species. So we're going to move away from our simple gas species and on towards liquids and solids. But mostly we're going to be spending a lot of time on when one phase will become another. So in order to do this, one of the things we have to watch out for is terminology. Because it turns out that physical chemistry specifically has a lot of very unique terminology when talking about with phases and phase transitions. So some of these may look like phrases that are used in common parlance or even other branches of chemistry. They're going to have very specific meanings when we use them. So a good thing to start with is pretty much the center of this chapter, talking about states. So state is one that we brought up before. So again, it's going to specify a species that has a certain precise set of physical properties. So if all the physical properties of a substance are identical, the two substances are said to be in the same state. And again, we define these by our state variables. So these are the ones that we've been defining a lot through thermodynamics. Pressure, volume, temperature being classic, but also things like moles, molar volume, entropy, molar entropy, all of those big sets of variables we've been talking about. Most of these are state variables. And again, most of our state variables are also going to form some sort of state functions because again, they only depend upon the current or initial and final states that we're talking about. The next one is also one that people tend to misuse a lot, and that's going to be phases. So something is said to be in the same phase if it has a uniform chemical composition and an identical state. So as soon as the states start differing in between two species, or the chemical composition changes. And it's the fact that both of these have to be identical that essentially adds in the little hiccup when we're talking about phases. Because you can have two species that have the same chemical composition. For example, diamond and graphite, they're both carbon species, and more importantly, both pure carbon species, but they have a lot of different properties, such as, say, they have different densities and different molecular arrangements. So while the chemical composition is identical, the states differ, and this means that they form different phases. And this will hold for any set of allotropes. So again, allotropes is our phrase for different configurations or arrangements of species. And when we're talking about allotropes, we're almost always talking about solid allotropes, such as diamond and graphite. But we'll encounter several other very unique sets of allotropes as we move throughout the chapter. Then the other thing we should also watch out for is when I use the word constituent. So a constituent species is going to be any chemical species that's present. So for example, if I go ahead and throw salt water, so sodium chloride, into water, I've got three separate chemical constituents because my sodium chloride immediately separates out into sodium, chlorine, and water. So I've got three different constituents. However, this is going to be slightly different from components, which are going to be chemically independent constituents. So while I form two constituents from my sodium chloride, sodium and chloride, if I know the concentration of one, I know the concentration of the other. So these two aren't going to be independent. So soon as instead, chlorine is going to be dependent upon sodium. So despite the fact that I have three constituents, I'm going to have two components. We can also imagine this getting a little bit more complex. So for example, what would happen if I threw calcium chloride along with sodium chloride into water? Well, then I'd have four constituents: calcium, sodium, chlorine, and water, but I'd have three different components. sodium chloride and calcium chloride and water. Because as soon as I know sodium and calcium, I immediately know chlorine. So it's not truly independent. And this is one of those things that can get a little bit messy in practice. So it's very important that we have the terminology ahead of time. So some of the other things we're going to want to focus in on is less about the individual states and species that I'm examining and a little bit more about what they do. So we're going to be focusing a lot on phase transitions. So these are the same thing as phase equilibria. So this is going to more or less just be a phrase to describe when two or more phases are present simultaneously. So the classic case is actually again with water. If I have liquid water present, this means I almost certainly have water vapor also present. And if these two species, so that means there is a phase transition taking place. And if I allow these to rest infinitely, so they come into equilibrium, this will be known as a phase equilibria. And so this is actually a very important set of terminology to know. However, because we often make use of phase diagrams to demonstrate where phase transitions occur, on these phase diagrams, we call these phase boundaries. And these are essentially going to be lines that denote where a phase transition or a phase equilibria occurs. So where I'm going to have multiple phases present. And we also have a couple other sets of terminology that help describe these phase transitions. So it turns out most of the time, if I have a liquid present, the gas is almost always present too. And so if I let my liquid rest long enough, it will reach what's called the vapor pressure. So this is more or less just going to be the partial pressure of the gas over a liquid once we get to that equilibrium mixture. So again, with an infinite resting time, because we're still on thermodynamics and haven't focused in on the kinetics or non-equilibrium states. However, there's one very useful point that we should make note of, and that's going to be the boiling point. So a liquid essentially ends up boiling when it starts releasing vapor at a pressure greater than the pressure essentially keeping the liquid down. So that pressure keeping it down is going to be our external pressure, and most of the time it's about, say, 1 bar. It's about 1 bar. And at a pressure, say, if the vapor pressure starts exceeding that 1 bar, then what I'm doing is I'm generating gas inside my liquid that's going to push the liquid up, and this is where boiling occurs. So the temperature at which that first happens, so when the vapor pressure equals 1 bar or 1 atm, if I'm using standard ambient temperature and pressure or standard ambient conditions, is going to be our boiling point. And this is one of those things that's very important is to denote when I'm talking about a standard boiling point of 1 bar or a normal boiling point of 1 atm, because these will give us slightly different different temperatures, slightly different boiling points. And it's worth noting that the boiling point can actually change significantly as I move to different conditions. So for example, if I look at, say, the normal boiling point, so that's 1 atm of pressure, then my boiling point's at 100 degrees C. However, let's say I go way up into the Rockies. So I want to go ahead and make bread up in Colorado Springs. Well, up in the Rockies, it turns out my atmospheric pressure drops down to 0.82 atm. And when I do this, it turns out that that actually lowers the boiling point of water down to about 95 degrees C. And it turns out that that's enough that there's a reason why you can find cookbooks exclusively for high altitude conditions, because that is going to significantly change things like cook times, as you're going to have to give yourself a little bit longer for everything to cook, as it's not going to be quite as hot. So again, things that you should watch out for in real good practice. However, it's important to note that a phase transition in between a liquid and a gas isn't our only kind of phase transition. We also have a phase transition in between solids and liquids. So this gives our melting point or our freezing temperature, also known as the temperature of fusion, because it turns out we don't have enough phrases. And so this is essentially going to be the temperature at which a substance melts. And it's worth noting, by convention, we're almost always talking about when it melts under 1 bar of external pressure. Because it turns out that this pressure too will actually be, this temperature too will actually be sensitive to the pressure conditions that we're working under. And then finally, in our sets of terminology, we have 2 extra very important points that are really going to help define a species. And these are the critical temperature and pressure. So we've already seen this before when talking about gases. So this is going to be essentially that temperature at which a gas is at equilibrium with both its liquid and its supercritical state. And this is a great reference point because since I have 3 different phases in equilibrium, it's defined by a single point. And this makes it a great, as we've seen previously, this makes it a great reference point when talking about gases. However, there's also an additional point which can really help define our liquids, gases, and solids, and that's the triple point. So triple point is when a liquid, a solid, and a gas are all in equilibrium with each other. And so this is a great reference point when trying to figure out where our other phase transitions occur. And again, we can really illustrate the importance of these triple points by making use of something called the phase rule. So a phase rule essentially is going to be a way of telling us about how much freedom a substance or a set of substances have. So we describe essentially the freedom of a species to move around in essentially temperature, pressure, and volume space by talking about its variance. So the variance is, again, the number of state variables that I can change independently. So we've seen this, say, for a gas, where I can go ahead and change the pressure and change the pressure independently, and then the temperature and volume will change accordingly. Or I can change the pressure and the temperature both independently, and then I'll figure out the volume. So we've played around with this idea of variance, but never exactly the phrase. Well, it turns out that the number of degrees of freedom or variance we have is going to be dictated by the number of components present in a system and the number of phases present. So if I have more components, I'm going to have more variance. If I have more phases, well, this is actually going to constrain the number of degrees of freedom I have. So if I look at a system where I say have pure water vapor, so I have one component, one phase, and plus this 2, I have 2 degrees of variance. So this is the reason why I can change pressure and temperature independently, but I can't control volume at that point. Because again, according to the ideal gas law, as soon as I know pressure and temperature, then the molar volume is intrinsically already decided. So this is going to be true for all species. If I have a pure species and a single phase, it's going to have 2 degrees of freedom it can move about in. But what, say, happens if I have, if I know that I have liquid water and water vapor both present? Well, at that point, I still have one component, but now I've got 2 phases. And that means that I'm only going to have a variance of 1. So if I know that I have liquid and water vapor in equilibrium, then it turns out as soon as I know the temperature of the system, I also know the vapor pressure of the system. It's already been decided. And if I say I'm at my triple point, where I have solid, liquid, and gas all present, I still have one component and 3 phases now. So this gives me a variance of 0, which means that I have no control over where that triple point occurs. It is literally a point. It's no longer a line, or it's no longer a free two-dimensional space. And so this is actually a fairly useful rule when we're looking at our single component systems. However, it's going to become a lot more useful next chapter when we're talking about multi-component systems, where I'm looking at mixtures, because then this will greatly help me figuring out how many degrees of freedom I have to move about in. And we'll spend a lot more time with the phase rule later. However, one of the things I kind of want to finish up with today is talking about one of the fun applications of the phase rule, which is our good old friend, the phase diagram. So you may have seen some of the phase diagrams in, say, high school or even general chemistry, where it's going to dictate under what temperature and pressure conditions a gas will occur, a solid will occur, or a liquid will occur. And most importantly, where all of our phase transitions end up occurring as well. So this, for example, is our phase diagram of CO2, which is fairly helpful, as CO2 as a gas is toxic, as a solid, it's a great coolant, and as a liquid, it's actually under fairly restricted conditions. And as a supercritical fluid, it acts as dry cleaning agent, because who doesn't love a nonpolar system that's as thick as a liquid but moves like a gas? Great for cleaning. And so when we're looking at these regions, what we're going to find is several of these terms and regions we've talked about, especially in mind of the phase rule. So for example, if I have a gas, I can have a temperature and a great number of different pressures. But as soon as I have any liquid, I have any dry ice present, then it turns out that I'm going to be constrained to be along this phase transition. So as soon as I know, say, the vapor pressure of the CO2 coming off, I immediately know the temperature of that CO2, because there's only one point at which these substances are going to be in equilibrium with each other. But this still does give me 1 degree of freedom. So I can have a range of different temperatures, but as soon as I know the temperature, I know the pressure it corresponds to. If I have a gas phase CO2, I may know the temperature, but there may be a great number of pressures, vapor pressures it may contain. And similarly, if I have a solid, well, it turns out that I may know the pressure or the temperature of the solid, but as long as there's no gas, then it's perfectly defined. Now, in practice, it's worth noting that as long as you're under equilibrium, there will always be some gas being released from a solid or a liquid. So solids or liquids are very frequently found along these phase transitions, which is one of the reasons why we greatly appreciate being able to describe these phase transitions, as it's going to tell us a lot about the solids and liquids. However, if I have a gas and no solid or liquid, this is actually quite common. And at which point I'm going to usually describe it with one of the gas laws we defined earlier. So this essentially gives us a brief summary of what we're going to be looking at this chapter when talking about phases and phase transitions of pure species. Next time, we're going to focus a little bit more on a special case, and that's going to be our good old friend, water. Till then, take care.